Numerical solution of ordinary differential equation. First order initial value problem of ordinary differential equation can be written in this format. This is a format of the first order differential equation, and for given initial value. These are the two examples. The rate of y is equal 3y plus 1 for given initial value at time 0, y equal 1. The second example is a time variant first order differential equation, because the time function also there. Then this is a first order differential equation as a given initial value at time 0, the y equals 0. Then for numerical methods, always the time steps can be estimated. That means the n means the present point. That means n the present point can be estimated the previous time and plus the time step is there. There are some examples for numerical methods for ordinary differential equation. So basic methods are Euler methods are Runge-Kutta methods. For Euler methods, forward Euler, backward Euler, and modified Euler. Runge-Kutta also there are the few methods are there. The second order, third order, and fourth order Runge-Kutta methods can be used to solve ordinary differential equations. Here in this lesson, we are going to learn the fundamentals of Euler methods. Then later on, we can elaborate that knowledge to understand Runge-Kutta methods. When we consider the forward difference approximation for first derivations, then we can see here the derivations can be approximated. That means the forward value and the present value divided by the time step. H is equal to the time step, and n plus 1 and present the time value is there. H is the time step. Then the first derivatives can be written in this form. Then we can rewrite the above equation to take out y n plus 1, which we need to estimate by using present value. That means y n is a present value, then y n dash mean in the derivation of present value multiplied by h. That means y n plus 1 can be estimated from the present value and the derivation of present value. Then yn recursively calculated by the series of equations. And if you know the any initial value, the y naught, if you know the y naught, we can recursively calculate it yn, y2 up to yn. This is the most simple method we are calling. This is a forward Euler method. Shall we try to understand forward Euler method by using this example? This is one example. The time variant example is there. The derivation of y is equal to ty plus 1 at a given initial conditions. That means at time 0 y equals 1. Then we are going to estimate the values from 0 to 1 that's a time scale. The time step here we considered here 0.2 pi. Then for t is equals 0 and y naught equals 1, then we can use the forward Euler expression there. That means y1 can be expressed y naught plus and the derivation of y at the present point and multiply by the time step. Then we can use this equation here. The y dash is equal ty plus 1 there. Then we know that there's a present derivation of that function. Then h is the time step. Then this is the value for y1. Then at the t equals 0.5, then we can use the y1, which was estimated from the previous step. Then we can find out the value for t2. Then this is the value here. This is a graph of the solution. Is the exact solution with the analytical solution. Is a forward dual solution with a numerical solution. You can see the forward dual solution is underestimate with reference to the analytical solution. These values are estimated from 0 to 1. This is backward Euler method. The backward difference approximation can be used to find the first derivations. This first derivation can be expressed as the present value minus the previous values divided by h. Here we are using previous values. That's the reason as the backward Euler. Now this equation can be expand up to this equation. Then yn, the present value, can be estimated by using the previous value. But here we need the derivation of the present value. There's the main difference with the forward method. Now the first derivation of the present value is here. Now the yn is recursively calculated as follows. That means series of equation can be written as here. Then if you know the y0, then we can calculate y1. But we need to estimate the derivation at the point of y1. Then for a backward Euler method, we need some simplification to estimate the derivation at the y1. To understand backward Euler method, we can use this method to the same equation which we use for forward Euler method. There's a time variant equation. We know the value for the time 0, and its time step is 0.25, and we are going to estimate the value for the 0 to 1. Then to solve that equation by the backward Euler method, this is the equation for a backward Euler. That means the present value estimated by the previous value and the present the derivation of the function multiplied by the time step. Now that equation need to be modified because of the present the derivation is there because of yn and yn. Some terms of y also may be there. Then this equation can be modified to estimate yn by using yn minus 1. Then so that we have for time 1, that means time equal 0.25, then this equation, the value can be estimated. These are the estimated value for each time step. If you know the value for y1, we can estimate value for y2. This is the value for y2. Then this is the y2 value we can use to find the y3. Then this y3 value can be used to find the y4. These are the estimated value from backward Euler method. You can see here there's a graph, the solution. This blue line is the analytical solution. The red line is the numerical solution by backward Euler method. Now you can see here there is a overestimated. The backward Euler is overestimated. The forward Euler is, can you remember, that is the underestimated. Modified Euler method. We can eliminate drawbacks of forward and backward Euler method by using modified Euler method. Modified Euler method is derived by applying the trapezoidal rule to integrating this part. That means the mean value of the derivation of the y n plus 1 and y n, then we can say here this value we can take on from the mean values from backward and forward Euler method. Then if the function is linear, y n plus 1 can be estimated same as backward Euler method, but that function is non-linear. These values need to find from other numerical methods which we use for nonlinear equations, such as successive substitution methods. To understand modified Euler method, we can use the same equation as we use for the forward and backward methods. Then now here, now this is the equation here. This equation can be simplified to obtain yn out of yn minus 1. The derivation of yn is there. Then when we substitute the equation for the derivation of yn, then the yn terms, some of the yn terms need to be in the right hand side. Then you can see here, now this is the most simplified equation. The yn can be expressed by yn minus 1. Now this equation can be used to get solution of this equation. After getting all solution from 0 to 1 from modified Euler method, this is a graph, the solution. You can see here. Now by using modified Euler, with compare with the exact solution, there's an analytical solution. You can see here, this now that's almost the same as analytical solutions. That means it's a comparison of the forward and backward modified methods. Actually, the modified method may be more accurate to predict the order differential equations. Second order Runge-Kutta method. This equation of the second order Runge-Kutta method, yn plus 1 can be presented by the yn plus. There's an integration of that function from tn to tn plus 1. Then that integrations, we can use the trapezoidal rule of integration here. Then here is the value, the y bar n plus 1 is there. That value need to be estimated from the forward Euler method. So that now that equation can be expand by substitution the forward Euler equation here. Now that is the more standard form. You can see here the yn plus 1 is equal to yn. So k1 plus k2 is there. The k1 and k2 can be expressed in this form. This third order Ranka-Kutta method. In the third order Ranka-Kutta method, we can use in the Simpson one-third rule to integrate that f function. That integration we have to use Simpson's one-third rule. Now in this method also yn plus half need to be estimated from the forward Euler method. Then here is the sum, the forward Euler equation need to be used to estimate the yn plus 1. Then it is can be presented in this format. The yn plus 1 can be present, yn plus the 1/6, and there's a values are there k1, 4, k2, and k3. Now this k values we can present in the k1, k2, and k3. There's a forward Euler also need to be find these values k2 and k3. This is fourth order Ranka-Kutta method. In this method, Simpson one-third rule is used to derive this equation. These four terms are there: k1, k2, k3, k4. Then these four terms can be expressed by these four equations. H is the time step. Now this the function is there. Then you can see here the k1 is coming there, the k2 also coming there. Here that is the substitute by recursively the k1, k2, k3, k4 can be estimated. As well as for the fourth order Ranka-Kutta method, we can use Simpson's 3/8 rule. This is the expression by Simpson 3/8 rules. Now same as previously, k1, k2, k3, k4 terms can be estimated by these four equations. To estimate these values, we need to use forward Euler method. Then for a fourth order Ranka-Kutta, Simpson one-third rules as well as Simpson 3/8 rules are used. Then we need to think about the more suitable method for the applications. That means depend on the applications, the most suitable numerical method should be selected.